All right, welcome back. So between here and lunch, we have a talk and then a panel discussion, and so should be fun. But really, actually, very pleased to introduce Dr. Lownik to the FlowTex world. He's been working for a while now, actually, on applying machine learning and AI to spectral flow cytometry. He has a couple patents and is actually coming to us with a very timely message around what we're going to talk about later today in the panel. And so, Joseph, thanks for joining us. I don't know where you were trained, but I'm sure they trained you well. He's a physician scientist and hematopathologist, and his work has been in spatial biology and specifically on the dynamics and influence of tumor biology, including the spatial organization and metabolism of the tumor microenvironment. So we're excited to hear what you have to say. Welcome.
Thank you, Marcia, for the introduction and all the organizers for allowing me to speak today. Oh, oops.
Oh, wow. But you don't have it, like if you use your mouse, just go on.
I'll just, won't even let me click forward.
It's gonna be on the desk. Hold it, your mouse like this way.
Oh, there we go. Okay. It's not advancing, no.
So we are. This is in the Zoom.
All right. Thank you. I have a few disclosures, just some patent applications on some of this work. So just an outline, I'm going to be talking about how we adopted spectral flow cytometry into our laboratory. Some of the challenges with large panels, this has kind of been discussed already. The implementation of machine learning for cell typing and the utilization of a decision support system in the clinical flow lab, and automated quality control. Come on. All right. So prior to switching over to spectral, we had 3 10-color panels that we ran on every sample that came in for the most part, and then a viability tube. And as you look at this with all of us that have been thinking about spectral, there's a lot of redundancy for backbones between these tubes. We have CD45 in all of them, CD19 in the majority, and CD5. And we decided that with spectral, because we got more channels, we decided to add a few more fluorophores to reduce some of our add-on tubes, as well as discrimination for some populations for MRD analysis downstream. But this really allowed us, we switched to the Cytometry Northern Lights, which was a 3-laser system. We ended up stacking kappa and lambda onto CD4 and 8 and ended up with 29 colors and 31 markers in our tube, which kind of stretched the limits of what a 3-laser instrument can do, but we made it work. So with large panels, there comes a lot of issues. So classically, we think of gating in biaxial plots, and we'll go for more granular and granular populations until we find the populations that we really care about for making a diagnosis. And if we think about biaxial plots that we can make with just normal flow cytometry data, so if we have 4 fluorescent channels and 2 scatter channels, that's 15 plots, and this increases very quickly as we increase our marker count. And when we get to 31 markers, we're talking about 528 different plots you could start to visualize. And this, it really isn't a linear relationship, it's more of a quadratic relationship. So this complexity really can become daunting when you start to analyze this high complexity data, and when you really want to look at all these markers in this high complexity data. So with the conventional 10-color that we had, manual analysis and gating was feasible. It was time consuming. Some of our CLSs would spend 20, 30 minutes on a case going through it. So it took quite a bit of time, but it also had a lot of limitations. We had to do inference between different panels. So CD16 was in our myeloid tube, so we can't really look at it on NK cells where we actually have CD2 and 7 on our T cell tube. And then, but the one thing is 10-color flow is really standard for most cytometers. And the spectral panel really allowed us to improve our ability to remove inference between different populations because everything is in a single tube, but it really caused complexity issues in our analysis. And then we also had issues with unmixing that we need to think about. And then panel design becomes really important when you start to think about those unmixing. So with spectral, we increase our parameters, we increase our ability for that detailed immunophenotyping, but it really increases the interpretation complexity and time that's required. So we wanted to try to bypass this, and we actually started this before we switched to spectral and did this with our old Navios instruments with the 10 color panels. But can we use machine learning for our cell typing rather than any sort of manual gating whatsoever? And the way we do this is we took our raw FCS files from our instrument. We do data transformation and clustering on these samples to find unique populations at a very granular level. So in our training data, which is hundreds of files, we're talking around 120 different unique clusters that we're identifying. So these might be 20 T cell populations, 15 B cell populations, but they're very granular populations, which allows for us to then train machine learning models. In this case, we initially were using random forest, but moved to XGBoost just for a little bit of bump in accuracy. But what this allows us to do is any new sample that comes in, every single cell gets run through these machine learning models and can be classified to a specified cluster that we already predefined with annotations that are clinically relevant. So we can think about this in the sense of if we have clusters 1 through 7. Clusters 1 and 2 might be CD4 T cells. Cluster 3 might be a CD4 T cell population that has dim CD7. We can group some of these so we know all of our CD4 T cell populations can group together. All of our T cells can group together. All of our lymphocytes can group together. So we classify these populations at multiple levels, which really allows us for true clinical implementation from these machine learning identified clusters. So at the cluster level, which is what we're actually predicting, this is a little bit old. It was about 95% accurate, but once we switched over to XGBoost, we're actually about 98% accuracy. But when we think about the clinically relevant population annotations, we're above 99% accurate on all of our predictions, which is pretty impressive, I think. So what can we actually do with that data? So we're now in an automated manner, we have identified all of our cell populations that are clinically relevant. So we decided to actually wrap this into a decision support system that takes in all of these population frequencies, all these population marker expressions, and interprets it as if it were a hematopathologist. So this took a while to kind of work the kinks out and think through it all, but we essentially set logical rules to think like a hematopathologist would think. So we're an adult hospital for the most part. So about 98% of our cases, 99% are adults. So we do a lot of lymphoma workups, less TALL, so we don't have any of those, but we set the thresholds based on what we would actually do if we were working up a case with manual gating. So we can set rules, what's an increased CD4 to 8? What's a decreased CD4 to 8 ratio? What populations would we call out as being possible LGL populations? We can set the same thing for all of our myeloid lineages. So we can set all of these rules, and because we're identifying these populations in a rapid manner, it just automatically feeds into this decision support. And what this does is it allows for an automated output of typical two-dimensional biaxial plots, but everything's colored by the machine learning classifications. I can output automatic interpretations based on population frequencies and whether or not abnormal populations are detected. It'll give suggested comments based on what was found, so the immunophenotype of the abnormal populations. It'll give a suggested comment whether it thinks it might be CLL or MCL, what follow-up tests might be required, because we can't make all of the diagnoses off of flow cytometry without ancillary tests. So it recommends additional testing to be done. And in this particular case, the kappa and lambda surface light chains were very dim. So it actually recommended to our technicians to automatically add on our cytoplasmic panel so we could discern what the light chain was for that. It also outputs an automatically generated report, which gets uploaded to our LIS. And as you can see on the top here, we actually do not give a diagnosis. That is the one thing with the system. We refuse to give a diagnosis because we do not a lot of diagnoses can be fully validated or verified by just flow cytometry and require ancillary testing. So we chose to not fill that in because as soon as we give a diagnosis that's wrong, someone doesn't verify it, the game's over. So it has to be filled in by a pathologist. So this is just an example. For the sake of time, I'm not going to go over how we detect monotypic B cell populations, but it's very good at finding low-level monotypic B cell populations in a background of polytypic B cells based on how the actual clustering works. And you can see in this case, the pink population is what it's flagging as being abnormal. And then the blue are the polytypic backgrounds. All right, so what I'm going to spend the majority of the time talking about is the automated quality control that we're trying to implement with our AI-based system. So as was alluded to earlier, spectral flow cytometry, while it has all of its advantages, has a lot of issues with unmixing, especially on a day-to-day and sample-to-sample with day-to-day and sample-to-sample variability. We see this a lot in our far red channels where we see day-to-day drift in our spectral unmixing. And how do we actually start to deal with some of those issues is what I'm going to try to talk about here. So as Paul and Stacy were saying, it's one of the nice things is we can actually implement viability dyes into our panel, so we automatically can exclude dead cells. We do not have a nucleated cell dye, so that's something I'm actually going to try to take home with us. I like that method, but we can automatically exclude dead cells. So this is just a very simple thresholding that can be done, but it can be done in an automated manner without a traditional gate. We can automatically exclude doublets, and this is just based off of a simple linear relationship between the forward scatter height and area aspects. And then we have an automatic fluidic aberrancy detection, which is just a modified version of the Flow AI algorithm. So we optimized it for a little bit better computational efficiency on our systems. But it's essentially detecting any aberrations in fluidics and excluding those populations from the analysis, and then plotting which groups were actually removed so you can look at that downstream. So these are all pretty simple methods, but they're automatically implemented into our workflow. One of the nice things about the Cytec instrument is it collects scatter off of both the blue and violet laser. And there's actually, if you look at the linear relationship between the side scatter off of those two lasers, you can very easily detect red blood cells because they have a different pattern than normal nucleated cells. So we can automatically exclude those cells very easily. And then one of the things we're building into our system, we haven't fully implemented this yet, but the new software I'm working on is going to implement this and keep it in a updated manner, is longitudinal tracking of antigen expression. So this is something we can think about if you come from a clinical chemistry background, is there is very good like LJ plots of all of the different readouts, but we really do not have that in flow cytometry. And I think a lot of it has to do with would have to come from gated data. We can't use ungated data for tracking these things longitudinally, but because we are identifying these cells using machine learning and very rapidly, we can actually take the median or mean intensities of all of the unique cell populations for each marker, and we can start to track these over time and start to track if there's any drifts in these. And not only can we track the mean or median expression of the markers, but we can actually start to track the unmixing and compensation error that is occurring on a day-to-day basis. And this is something I'll talk about a little bit later. So this is just CD3 on different T cell populations and CD4 and CD8 on the different populations. And this is just individual files that are making each of these little notches. But if we start to think about, do we lump these on a day-to-day basis? And like, how do we start to group these? So this is something we're working through right now. And then compensation. This is really one of the big questions. So I think this really stems a big debate. Do we do compensation, which is kind of what the Cytec method is, versus do we adjust the unmixing matrix? So both of the platforms allow for adjusting of the unmixing, whether that be like more of a traditional compensation method or whether that be adjusting the unmixing. And this can be a pretty unwieldy task and take a lot of training and a lot of time if you're doing it on every sample. And we, in our lab, see pretty significant, not significant, but we see day-to-day drift, especially in the far red channel. So it's something that needs to be addressed. It doesn't limit our data interpretation with the way it's at, but you do notice it. So it's something we're trying to work through. And how do we do this in a robust manner? Because training somebody to understand the difference of compensation or a spillover on mixing issues and like true biological phenomenons takes a lot of time, and it's something that if it's not done properly can really skew the interpretation of the results. So this is just a two-dimensional plot of some of our data. So we plot everything on an arcsine transformed axis, so it looks a little bit different than people who are used to by exponential. But this is CD19 versus CD2, where blue are T cells, red are B cells, and purple are actually just monocytes. And just for reference, CD19 is in a violet 760 channel, CD2 is in a violet 790, so pretty spectrally similar. There's a good amount of overlap. And on these far ends of the detector channels is where we see that drift. But you can see pretty clearly here that this T cells are being or the unmixing is not performing perfectly between the two, and we see it both on T cells and B cells here. So we tried to think about what is a way we can do automated compensation or unmixing it, more so automated compensation on these samples. So we could think about this in a few different ways. One is we could just take the centroids of all of these populations or the median intensities, and we could think, okay, we have a dual positive or a single positive T cell population, a single positive B cell population, and our monocytes are double negative. So we can get these populations, we could start to think, okay, if we just take the slope of the double negative to each of the single positives, can we just correct that to a linear, like a relationship of 0? And these curves look, they look like curves rather than straight lines because it's on the arcsine transform scale. So that's why it's not a linear, like a perfectly straight line, just for reference. But we can just think about, we can calculate that with using a simple relationship for calculating slope based on the XY and knowing the single positive and double negatives. And then we can actually correct for the Y prime for each cell based on the adjustment factor that we calculate for the slope. But as all of us know who have done any sort of unmixing adjustments, if we do if we change one unmixing pair, it affects everything. So we can't just say, okay, calculate the slope for all of the pairs, and then we're going to correct all at once. It just does not work because if you adjust one, it's going to have a ripple effect through the entire matrix. So we took the approach of what if we do an iterative processing? And the way we do this is we first look at all of our combinations of fluorophores. So this is just the markers, not necessarily the fluorophores here, but for reference, CD5 is super bright 436, CD123 is BV 421. So very spectrally similar, and they have a high similarity. So we get all of the pairs of our similarity indexes, and then really we have 812 combinations. And when we really do all the possible combinations together, and it's a wide range of similarity scores. So to do this iterative process, we really have a few prerequisites that we need to think about. One, population of fluorophore pairs, and these can be either manually defined or we've worked on some automated methods for defining these. But what I mean by this is what targets are we looking at adjusting? So CD5 and CD123. What would be our source cell would be a T cell, and the double negative would be a mature B cell, unless it's a CLL-like cell. And then we could think about CD3 and 117. Also, we could use a T cell as our source, and then the mature B cell would be our double negative population. And then what is the minimum similarity score that we actually want to work on for those pairs? Because we don't necessarily want to go after all 812 pairs. So we think about the ones where they have no similarity, so it's 0. We really don't expect there to be issues between those, so we can set a threshold for that. What is the maximum slope that we're going to be allowing to be abnormal? Well, we're not going to get everything to 0. So do we say 1% off? Is that okay? 5%? Where do we want to cut that threshold? And I'll show that a little bit later. How do we actually adjust that slope? Do we adjust that slope all in one fell swoop for each marker? So if we think about the equation of how we're actually adjusting slope, we can set this factor K into it so we don't overshoot. We can actually set that to be, say, correct 50% of the slope issues at one time. What is the maximum number of iterations that we're going to do? So this is more of a computational question. And then what's the minimum number of cells in a population that we're going to require to allow to calculate this slope? So the way this iterative process works is we calculate the slopes for all of the specified pairs. So say there's 100 pairs, we're calculating 100 slopes using a robust linear model. We correct just the single slope with the highest, or with the highest slope pair with the specified K, we correct that. We update all of the values based on that update, and then we recalculate all of the slopes again, and we repeat this process for however many iterations that we talk about. So with a sample with a couple million cells, and if we do 1,000 iterations and we're saying 0.1% is our threshold, this takes about a minute or two. It's pretty quick, it's parallelized, so computationally it's quite efficient. So how does this actually look when you start to think about the thresholding that I was talking about? So this is CD8 versus 16. In blue are T cells, and then in green are NK cells. And for reference, CD8 is on APC, while CD16 is Alexaflor 647. For those who are on conventional flow cytometry, these cannot be used together, but on spectral, they can be unmixed pretty nicely. But this is the area where we start to see our day-to-day drift. So if we set a 5% threshold, we really don't see any correction on this. We set a 2.5% threshold, we can see that this is starting to improve that compensation. And the more we adjust that threshold or bring that threshold down, the more we actually start to improve. We can see that we get further improvement. So we've been working on validating this to bring into our actual workflow that we're using for our automated analysis. But we started to see a few issues that started to come about. And one of those actually had to do with the idea of background autofluorescence. So we don't, at the time, we hadn't been subtracting autofluorescence from our samples just because it was another layer of complexity, and our CLIA director wasn't excited about it at the time. We've since moved forward with it, but we ran into the issues when you think about something like a monocyte. It has a different autofluorescence. It might just have some autofluorescence that basically affects the slope when you start to think about 2-point connections between this double negative monocyte population and the T cell population. You can see that what's happening is if we look at this line, it's actually being overcorrected just because of the fact that the monocytes have a high background autofluorescence. So when we try to correct with that using monocytes as our double negative, we really run into the issue of an overcorrection on the T cells and an undercorrection on the B cells. So the other issue that we had with that is it's really, you're not always going to find a double negative population for the combination you're looking for, and it might be hard to find a single positive. So we thought about, can we actually work with the variation of expression for CD2 here and the variation of expression of CD19? Can we just focus on those populations and the variation of expression on those to then calculate a new slope without the requirement for a double negative population? And you can see that the slope line here really characterizes that a lot better than the previous one, where we required it to go through the median of the monocytes as a double negative. So this is calculated with an overall least squares method, so a little bit different. But we can see that the correction of, so in reference, we have the dotted lines here are using the 2-point method, and then the solid lines using a 1-point method for correction. And when we look at the results for that, we get much better adjustment using the single population adjustment. So that's something we're currently working on moving forward and validating into our pipeline right now. So in conclusion, the implementation of spectral flow cytometry with large panels does require a lot of careful planning. And while you can throw a lot of colors into it, it really requires detailed planning, just like a conventional flow cytometry assay does. And then spectral panels decrease the inference and allow for a lot more accurate assessment of abnormal populations. We've been very happy with that. Machine learning really improves the workflow for cell typing interpretation. And then using that with a decision support system really allowed for significant labor and panel savings for us. So we have about a 30% decrease in add-on usage because of this. We've saved about 1 FTE time savings, and we only do about 5,000 tests per year. And this was strictly in the analysis time. And it's not that we let someone go because of this. We have been understaffed for a long time. So this was a nice thing and a very welcome thing for our CLSs. It's also saved a lot of time for the pathologists as well. Automated QC is definitely feasible and addresses a lot of the issues with daily variation and unmixing. And some of the next steps we're going through right now, validation of compensation adjustments using autofluorescent channels as well. So we find it difficult to run a autofluorescent sample for every single sample that comes through our lab because we use this for CSFs, we use this for fluids. So we use a single reference for autofluorescence, and that does get variation from sample to sample, so we can actually correct for that as well. And then finalize the full software integration of this entire process into a graphical user interface so that It allows for more interpretability and back-end understanding of what's actually happening. So the first implementation of this was all hard-coded into R. The current one's all hard-coded into Python. So we wanted to make this into an actual platform that is understandable for people and that a person without a computer science understanding can actually work with. So this software allows for, it has a clustering module, machine learning training module for making all your models to be able to predict, a longitudinal QC module, the pipeline and decision support builder, which I'll show, and then a gating and post-analysis worksheet. So you can gate like you would in any other software like FCS Express. So the clustering module allows you to cluster based on any group of FCS files that you can start to then find unique populations to train. The machine learning training module can then take in that cluster information. You can say what markers you want to use for clustering. It has built-in support for all different types of machine learning, random forest, LDAs, XGBoost, neural nets. It gives very detailed information on how your models are actually performing. So the accuracy, the F1 scores, confusion matrices of all your different populations, and then how it's doing for each population in its prediction accuracy. The pipeline and decision support builder. So I talked about a lot of this, but essentially this allows the user to say how FCS files are loaded, how you're doing your data transformations. All of these are built into small steps. They all have connected nodes where one of these will feed into the other on events. We can load annotations for clusters into it, and then the annotations get merged through that. This is an example of what one of those nodes looks like when you open it up to work with. So this is how we can set our monotypia calculation for B cells. So all of these things are dynamic and can be set by individual users. And then one of the issues we really encountered was we have all these machine learning annotations and probabilities that are being calculated, but we had no software that could actually take in this data to then be able to start to work with these machine learning annotations. So that was really the drive to build this software, but we essentially built an entire gating strategy, like a full software where you can gate, you can do population hierarchies, you can add in TSNEs and UMAPs into this, you can do additional clustering steps on top of your samples, but you can gate everything by the actual machine learning classifications. You can view probabilities of all the cells on what their max probability was for every level of annotation. So you can start to see are some of these population, this is what I'll talk about here. So how do we utilize the prediction uncertainty into our actual analytic platform? So if we start to think about if a new population comes about and has a low prediction probability, it might be something that's abnormal, and how can we actually start to utilize those types of things? So are the novel populations having that? And then can we do majority voting to kind of reclassify some low confidence cells? And then the next step is really trying to do some additional like beta testing with different sites on this software. A lot of people to thank for this. Sumi Kitahara, who's our division chief, worked with me a lot on developing the decision support component of this software and has been supportive of us getting spectral and implementing this into the clinical space. All of our CLSs have spent a lot of time on this. The hematopathologists have reviewed all these cases. We're very supportive of implementing the AI-based approach for our analysis. And with that, I'll take any questions.
Really great talk. I think you did a great job explaining it. I'm curious, Rui, some of the stuff that you guys are looking into, like understanding unmixing better, does some of that tie into any of what Joe just finished showing us? Or is it unrelated? Yeah. Sorry to put you on the spot, but it's a question I have.
Well, I mean, all this part related to the quality control. I think in research, it's a different aspect here. We're essentially looking for, we're exploring biology. We're trying to understand biology. So making these corrections after the fact is dangerous. I mean, in this case, I see a lot of value in especially. So my biggest question here, and I'm trying not to say too many things here. My biggest question here is more, you're doing this all using machine learning. You're trying to correct these artifacts that come from technical aspects like reagents that drift, instrument drift, etc. What if we put all this effort into actually trying to fix these things versus doing all this work trying to correct the lack of quality of the data?
And I'm going to tag one more thing on. So I love what you did here because you're actually showing that there's a problem, right? So to correct a problem, we have to show the problem. So then engineers go back and do what happens. And we're going to lead into this in the panel discussion that, in research, it's been about dimensionality. How deep can we go? On the clinical side, we're going to be coming and saying, how is this robust? How is it reproducible? How can we take it to CLIA and CAP? How can we anchor our hat to it when we're telling this oncologist, hey, this is what you need to go back and do for that specific patient? So maybe that's a comment more than a question, right? But these are the exact conversations we need to be having.
Yeah, and I agree. I'd rather fix the problem than have to adjust the problem. And I think it really comes down to starting to think about the standardization and everything. I mean, when we switch QC lot beads, our spectral libraries no longer make sense because our instrument gain settings are changing. So how can we, we've started to think about how can we not let the gain settings change on an automated basis, but rather we adjust that slightly too. Because I think, I'd rather fix the problem than adjust for the problem.
Okay, so to keep time, we will go ahead and have our panelists come up. Thank you so much.